Hello, Marauders, and welcome back. It's me and Greg the Grasshopper. Hello. And we're going to do conics this week. Conics is the study of cones. And cones are quite amazing because if you slice a cone in various ways, you get these very interesting shapes that are the shapes of the universe. All the past in the universe, so many things are based on the cone. Let's see how it works. Okay, conics. Yes, the cone. In class, I actually have a cone that's sliced, but we'll look at the book right here, and like you say, hopefully look at the photos on the assignment. Imagine you had a cone. Of course, how do you get a cone? It's how you slice it. And my grasshopper, he's going to help me out. Imagine I just had a stick, a perfectly straight line. How do I even create a cone? And why is there two cones back to back? If I took this and I started to spin it, that doesn't work too well on the camera. Imagine I were stirring something. So if I took this, I have to go slow and spin it faster and faster and faster. Do you see how that could make two cones back to back if I were to spin it around and around? The middle stays still, but the edges are turning around and around. That creates these two cones back to back. That's why I see two. And then how you slice it, if you were to slice straight across and look at what you get, we call the cross section, you'd have a circle. If you hit it at an angle, you get an ellipse, or called an oval. If you hit it this way, you get a parabola. And not just a U shape, it's perfectly an x squared, like y equals x squared. It's a perfect parabola shape. It's the shape of gravity. Think about the planets in the universe. There's circles, elliptical orbits, there's parabolic orbits. It's caused by gravity. When the ball goes in the air, it creates a parabola. And if you turn this a little bit straight down and hit the other cone, you get two back-to-backs. This is a hyperbola, or you can say hyperbola for fun, like I like to say parabola. But a hyperbola or hyperbola, it's two of these back-to-back. It's not two parabolas. It's a little bit different. It's more straight, curves, and then goes straight, kind of like a boomerang or an L. Straight, curves, and goes straight. Sometimes you might only see one, but this is back-to-back. When a straight edge hits a cone. In fact, if you want to see one right here, see this pencil? It's a cone, and the edge is straight. You see these little bumps right here? When the pencil sharpener and the straight edge hit this cone, those little curves are hyperbolas. So they're all around you. Okay, the circle is our first one. We learned about this a long time ago. We did the equation of a circle. It's actually the Pythagorean theorem. A squared plus b squared is c squared. Remember this? And what's a circle? All the points equidistant, means equal distance, from the center point. I did it here. I put this push pin in here with a string, and the string never changes length. And if I just went around, and I went right through my problem, you get a circle. Circle is all the points the same distance from the center. Pretty cool. And remember, we called the center H and K, and we put it right in here. And R was the radius. You don't have to solve anything, but if I put some numbers in here, like, let me bring this up a little. If I wrote x minus 5 plus y minus 10, you just kind of go, oh, okay. Well, here's H and K. There's the H. There's the K. 5 and 10. That was the center. And so this would be 5, 10. If I had a piece of graph paper, that's where at. This is where the center of this guy's spin is. Gears and wheels and everything. We could be working on blueprints. I had to say where that's at. And what is the radius? Remember over here, r squared. R squared is 36. You see that? So you have to go, okay, well, r is 6. Sometimes you get a number you can't take a perfect square root of, and you got to use like a calculator, right, as a radical. So in other words, the string length, my string here, at a radius of 6, no matter where I put my string, it's all 6 away. Every point is a distance of 6 away. That's the circle. We did this in the past. So let's go on to the ellipse. What is an ellipse? Okay, so now we have the ellipse, or you say elliptical, like elliptical orbit. You might have heard of a machine in the gym called the elliptical. It's like a bicycle, but instead of the pedals being on a round wheel, they're on an elliptical wheel. In fact, those are supposed to be pedals. Some professional bikes, for those professional Olympic people, they have an elliptical sprocket on their bike that helps increase the power stroke of their legs. So they're not wasting time going front and back, they're going up and down. Also called an oval. And how do you create an ellipse? You heard the planets are in elliptical orbits. This may blow your mind. Okay, the ellipse. All the points that are equidistant from the sum of the distances to the foci. Foci, that's plural of focus. These are the focus points. Okay, here's what I did. This string has 2 push pins. I have this piece of string. The string never changes length, but an ellipse is created this way, the official definition. Now, we saw before how the sun, or the earth, goes around the sun, and here's the sun at the center. But actually, the earth is not in a perfect circle, as you know. Nor is the sun actually at the very center of our solar system. What? The sun is actually at a focus point. Now, this string never changes length. I'm going to put my pen here. I'm going to try to do this the best I can. I'm going to start drawing. As I go like this, notice this string gets long, but this one gets short. I go like this, and I get a little caught right here, so I got to lift it up over. And I go like this, around, 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 around. You can like YouTube this stuff. So you like draw an ellipse. And of course, my string's getting a little caught here. Oops, there it's slipping. That's the definition of an ellipse. Sorry, my string got tangled up, but this would be perfect. Notice it's longer than it is tall. The center is right here. There's a center, but this could be the Earth. And where's the sun? The sun is actually not at the center of our solar system. The sun is at a focus point. It's off to the side. So not only do we go in elliptical orbit, the sun is kind of off to the side. Not much. The farther these are apart, the more and more elliptical it gets. If I got this all the way so it's a straight line, it would be really flat. If they're really close together, and I did this, it would be almost a perfect circle. In fact, if they get around top of each other, you do get a perfect circle. As they get farther and farther, it gets more and more elliptical. We have an actual word for that. We call that the eccentricity. And normally I'd have you calculate the eccentricity. Eccentric means like how much off of normal. Like that eccentric person, how much are they off of normal? The eccentricity of the orbit. But yeah, that's elliptical orbit. It's the sum of the distances to these 2 points. Maybe this string was 10 centimeters. So right here, it could be 6 plus 4. Right here, it could be 5 plus 5. Way over here, maybe it's 8 plus 2. But yeah, wherever it is. So it's interesting. If this is where the sun is, what's over here? There's nothing over there, is there? Yet, we get control. As we go around the sun, we actually speed up here. We go woo, and then we go slower, 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 slower. Real slow out here, and then woo, speed up. Comets do the same type of path. But there is nothing over here really holding the string in the solar system. So what is over here? Because to create an ellipse, you need 2 focus points. Some people think it's the anti-sun. What? Parallel universe? Other dimensions? Dark matter? Maybe there's another sun in another dimension that's holding us in orbit. Woo! Kind of spooky. Let's learn the equation of the ellipse. Okay, in the book, they do show kind of what I did with the string. You can see YouTube's. And it's interesting, these are called the focus points because energy actually focuses there. If you stood here in a room that was shaped like this and you talked, your voice would hit the wall, bounce off it, and go to this point. In fact, whichever direction the sound comes out of this point, everywhere it reflects, it heads to the other focus point. That's what these are trying to say. So you could stand here and whisper, and a person over here could hear you, but everybody in between can't hear you. It's a focus point. I show a picture of the statuary hall where a politician would use that to eavesdrop on other people at the other side of the room. And we don't say radius for the ellipse. We do have the center, and we say we have the major axis and the minor axis. Major is big, minor, small. So we have kind of like a long radius and a short radius. The corners are called the vertexes or vertices. We have the major vertices, and we have these up here, the co-vertices. It could also be the other way. Sometimes the major axis is up and down. Either way, major is big, minor is small. And I would not look at the book here. The book makes it look like you need two different equations depending if it's wide and tall. You don't. The book makes it really confusing. Let me just show you how easy this is to do. Okay, so remember the circle equation and h and k are the center? Well, here's the ellipse equation. H and k are the center, but here's what's different. Here's what's different. Instead of a radius, there's a 1. Always a 1. If there's not a 1 there, you have to do some algebra and manipulate it. But then underneath these are two numbers. I'm going to call this one a squared and this one b squared. These are the radiuses or radii. This is the a radius and this is the b radius. In other words, this one's under x, this is the x's radius, and this is the y's radius. Don't look at the book. The book makes it kind of confusing. Don't look at the book. The book thinks you need more equations. All you need is this one. Trust me, just this one right here. Okay, let me put some numbers in here so we can see how it works. Okay, so this one, now I didn't put a minus h and a minus k. Like I say, let's pretend the center is just 0, 0. So what are these numbers underneath? This is a squared, and this is b squared. It doesn't matter which one you call a or b. If you want to switch it, you can. This, though, is under the x. So this is the x radius. It doesn't matter if it's a or b or w, but the book makes you think you have to know that's a. But this is the x's radius, so a is 3. Over here, this is under y. This is the y radius. And in this case, we've got, whoops, I wrote 9, 25. B squared is 25. So what's the y's radius? Oh, the y's radius is 5. Okay, so let's draw it. I didn't put anything next to this, so we're going to start at 0, 0. That's the center. Okay, so what's the radius? The x radius is 3. So in the x direction, go 3. 1, 2, 3. 1, 2, 3. In the y direction, it says 25. That's the y radius. Go 5. 1, 2, 3, 4, 5. Looks like he's a tall ellipse. 1, 2, 3, 4, 5. Okay. And then now, just try to draw it in roundy as you can. Try to bring him up there and bring him down there. Ta-da! That wasn't that hard. I might say, so what's the length of the major axis? Okay. And what's the length of the minor axis? I will ask you these. The major axis is the long direction. Who's longer? This way is longer. That's 5, and this is 5. Do the whole thing. It's actually a diameter. So the major axis is 5 plus 5 is 10. The minor axis is short in this case. The minor axis is this way. Okay, so remember, major is always the long one. Major is big, like we got a major problem. Well, minor is small, like I'm only a minor, okay? Minor is small, so the minor, I'll do him in green. Here we go, minor, he's 3 plus 3, he's 6, okay? You could also figure out where the push pins go. If I were to draw this circle and use my string, where do I put the push pins? You put them at the focus points. There's a focus point somewhere over here and somewhere over here. The more oval it is, the more it is. I am not going to require you to find the focus points, but if you wanted to find the focus points, or as we call them, foci, the rule is the focus points, we usually use the letter C. C squared is a squared minus b squared. Whoops, I'm off the screen. Focus points is this right here. You go, what's this? A squared and b. It doesn't matter who A and B is. You have to pick the big number, take away the little number. Whoever's big or small. So it doesn't matter who A and B is. Ignore the book where they get like totally crazy and think you need to really care about it. just pick the big number, 25, minus a little number 9. 25 minus 9 is 16. Bring that up. C would be plus or minus 4. You would go 1, 2, 3, 4 would be exactly perfect. 1, 2, 3, 4. That's where the focus points would be, 4 away. And you could say, oh, 0, 4, and 0, -4. I'm not requiring you to do the focus points because we're distance learning. I could, what we would do in class, I'd even go backwards and say, I'm going to give you the focus points, you create the ellipse. Okay, but I just want to get you that far. Let's try another one. Okay, so here's a new one. And here's our form. Now I'm going to put all the numbers here. So first of all, let's look at the top part. X minus 6, Y minus 4. I'm going to ask you, where is the center? And you say the center, 6 and 4. That's X, that's Y. Ignore the minuses built in. If you saw a plus, then he'd be negative. So if it says minus, he's plus. It's an opposite thing. So we go to 6, 4. Here's my graph paper. So go over 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Boom, there's your center. Now, what is the x's radius? Look what number's here. What squared is 9? You're going to say 3. In fact, you can go plus or minus 3 if you want, because go in the x direction, now go 3. 1, 2, 3. I'm not to scale here. 1, 2, 3. Put a dot. So go 3 each way. 3 and 3, kind of like plus 3 and minus 3, go 3 each way. Make him a little bigger for us. And now let's do the other one. This is the y's. This is b squared is 16. It could be a, doesn't matter who a or b is, okay? Doesn't matter. You can call either one. Either way, this is the y's. B is plus or minus 4, so the b is going to go 4. 1, 2, 3, 4. Go up 4. Put a dot. Go down 4. 1, 2, 3, 4. Now, if I had graph paper, I could do this much nicer. But I'm going to do it like if you didn't have graph paper. And now, draw in your ellipse. Notice he's a little taller than he is wide. So there's these guys. And I try to connect him the best I can. And so if I say, how long is the major axis again? The major is the long direction, 4 plus 4, 8. The minor axis, how long is the minor axis? This little guy, 3 plus 3 is 6. And if you had to name the pieces, this is a vertex. It's easier to read if I did on graph paper, and I'm a vertex. These points out here. These guys are not as major. Like if this was an orbit, this is the farthest ones. These are not as important. They call these the co-vertex or co-vertices, and this guy's a co-vertex. And I'm not going to calculate the foci, but if you want to calculate foci, you do a squared minus b squared. And once again, it doesn't matter who a or b is, because if you say, oh, is this a and this b? Wait, I can't do 9 minus 16. We'll do 16 minus 9. Okay, you would just go c squared 16 minus 9. C squared is 7. C is plus or minus radical 7. You would say the foci are at a distance of radical 7 from the center. In which direction? Always the long direction. Just think about when I did my string. The foci would be, one of the foci would be up here, one would be down here. And once again, I'm not going to require you to name the point, but if you had to name the point, for those people who are a little more advanced, you would take the center, 6, 4, and say, well, I went up. So on this, I went up plus or minus radical 7. And that's how we'd actually name it. We'd say, okay, I'm at 6, up 4, then an extra radical 7 upward, and take off a radical 7 downwards, instead of me trying to figure it out on trying to read it. Pretty easy. I'll do one more. Okay, this time I drew it. You write the equation. Go ahead and pause the video. Can you write the equation? I'm going to set it up. Remember the format, x minus h squared, just like the circle, y minus k squared, equals 1. Divide, this is a squared, this is b squared. Or it could be the other way around. Doesn't matter. Okay, fill in the numbers. Replace the h and k with the center. What goes in for a and b? X's radius, y's radius. Pause it if you want. Okay, got your answer? Okay, so the center The center is 8, -2. So we're going to put x minus 8 and y, wait, minus a -2? How about we write +2 then? Use the opposite. X minus 8, y minus a negative is y plus 2. Now let's look at the x direction. The x goes 10, but you got to square it. 10 squared. Some people just leave it, but let's write 100. And the y is 7, so we would put 7 squared. Well, let's just change that. 49. And there you go. Ta-da! Okay, one last thing I forgot. The book has examples, and they kind of go, well, oh, he's a 0, 0. X is 3, y is 2. And so they kind of go through it here and say, yeah, so notice we went over 3, back 3, up 2, down 2. And there's the focus, which once again, I'm not going to require you to do. But let's say, what if you got one like this? And you go, wait, that's an ellipse? Where's the bottom? Where's the 1? As you look at this guy, you're like, there shouldn't be a 400 over here. So you know what you're going to divide by? 400. Divide them both by 400. Don't use a calculator. Well, what I could use a calculator. 400 over 400 is 1. What's 16 over 400? Here's what you do. Here's a neat trick. Divide it. You could reduce the fraction. Divide it upside down. Go 400 divided by 16. Upside down. 25. 16 goes in here once. 16 goes in there 25. 25 and 40, 400. 25 goes in there once. 25 goes in there 16. Okay. Just divide upside down on the calculator, you'll get these. And now you got it. And now you can make your ellipse. 0, 0, x goes 4, y goes 5. And they actually draw it over here. X went 4, y went 5. They found the focus points, and how? They did a squared minus b squared. Well, like I said, I'm not going to require you to do that. Okay, so that's ellipses. The book shows you some more about the transformations. You could see all their little drawings. And they even do some more that you can find. Real good examples that you just look at some of the drawings. This guy, where's he at? +1, -2. +1, -2. The x went 2, 2 dots away. The y went 3, because that's 2 squared and 3 squared, up 3 and down 3. There you go. Okay, and they show you some neat applications, word problems we won't get to in the homework. Remember, I only assigned to do part of it. You know you can see all my stuff. Okay, there we go. Next video is going to be the hyperbola.